Welcome back from the lunch to the first tech track of this CyCon. Machine learning as the way forward to defend against emerging threats. My name is Artur Slavrenos. I am technology researcher at CCDCOE, and I will be moderating this panel. My main field of interests are web and network security, and lately I have been focusing more on the network security research, which often results in huge data sets that can be processed by humans even in semi-automated way. So after considerations and investigations, I have come to conclusion that my and many other researchers can move forward only by applying machine learning techniques. And I am very grateful that I have colleagues that are much more knowledgeable in this field. Sadly, machine learning is not a magic bullet that automatically solves all the problems. It would be very nice. Its applicability is highly dependent on the problem domain and also experts. It seems that the approach of joining together machine learning experts and cyber experts is the most efficient way how to proceed, because these fields are very large and complicated, and becoming expert even in one is quite problematic. And today we are going to see machine learning experts that have joined their forces to solve cyber problems. In this session, first we will have Mr. Roland Meyer from ETH Zurich introduce us to their approach to detecting command and control channels. Our next panelist is Dr. Roman Graf from Austrian Institute of Technology, who will explore applicability of neural networks for Android application classification. And our third panelist, Professor Michele Colajanni from University of Modena and Reggio Emilia, will provide a closer look at addressing adversarial attacks against machine learning algorithms. As you just heard, we have very research-centered panel. We have distinguished speakers from 2 universities and 1 research organization. And before we start, just a few words about the format of this panel. We have 1.5 hours and 3 speakers. Every speaker has up to 20 minutes to present their research. After that, you will have chance to ask couple questions to everyone. So listen and come up with questions related to the specific presentation. And please keep the questions short and concise. And if you have something long format questions or discussions for specific topic, you can always find the authors after the panels till the end of CyCon week. And at the very end, we will have about 10 minutes of panel discussion. We will try to tie everything together, and if you have a topic you want to hear being discussed, you can propose it at the end. So first on, we will have Mr. Roland Meyer, who is PhD student at ETH Zurich. He is a part of a network systems group, where his research focuses on the security of computer networks. In particular, he works on solutions which leverage recent advances in network programmability to make networks able to detect and mitigate attacks and provide more security and privacy. Roland is presenting already 3rd year, and first one was in 2017 when he won Junior Scholar Award. His presented research investigates machine learning applicability for detecting of command and control channels in LogShield's Defenders dataset. Okay, please, Roland, the floor is yours.
Thank you very much, and I'm very happy to present our work on detecting command and control channels in the LogShield exercise here at CyCon. Most of this work was done by Nicolas Kenzig, and the project was done in further collaboration with Luca Gambazzi and Vincent Lenders from ArmaSwiss and Laurent van Bever from ETH Zurich. To start with, I'm sure all of you have heard headlines such as this one, describing large-scale cyber attacks against critical infrastructure. This is an example of a ransomware attack that hit many UK hospitals, or another attack that was targeting the power grid in the Ukraine. And apparently there was even a high-tech war here in Estonia taking place 2 years ago. And from a research point of view, from what we are looking at, these attacks are very interesting, or would be very interesting to learn from, but it's very difficult to get data. So data in terms of, for example, network traffic that was exchanged, and data that would be required to learn how we can defend against such attacks in the future. However, the last example was actually slightly different. Most of you probably realized that this was not a real war, but this was just the Locked Shields exercise, which takes place here every year. And in fact, it's the largest cyber defense exercise of its kind. And it is a red team versus blue team exercise, which means there is a red team running attacks against blue teams, which have to defend against the attacks. And in the case of Locked Shields, the red team is one central team, and the blue team are usually one blue team per participating country. This exercise runs at a very large scale with over 1,000 experts in the roles of these red and blue teams. And these experts come from all over the world. There are thousands of systems that are attacked, and thousands of attacks that are run over the period of about 2 days of this exercise. And the unique thing about this exercise is, compared to real incidents, that we do not only have the data in terms of the network traffic that was exchanged during the exercise, but we also have a ground truth which tells us what the attackers were doing, also what the red team was doing, and what the infrastructure was that they were using to run the attacks. This you usually don't have in the case of normal attacks, because the attackers will not tell you what they did. You only know what you found out yourself through forensics, for example. And the goal of our project was that we got the data from the Swiss Blue team in this Locked Shields exercise, and we wanted to develop a system that helped the Swiss Blue team, or blue teams in general, to improve their defense in the following years. And what we could already tell from the evaluation results that we got with our data is that if the Swiss Blue team had used our system in 2018, they could have discovered more than 80% of the command and control servers by looking only at data that was exchanged over about 30 minutes of the first day of the exercise. I will later present you more results from our evaluation, but first I would like to cover 2 other parts. In the first part, I will speak a bit more about Locked Shields and how it works from a more technical perspective. Then I will present you how our system works that takes network traffic and tells the defenders which of these flows are command and control flows, before I will present you more evaluation results in the last part. So a few more words about Locked Shields. I already told you that there are blue teams that have to defend their network, and such a network is fairly big. For example, it can be the one of a military airbase, which consists of industry control systems, of maybe air vehicles, of traditional client-server infrastructure, and so on. So we have many different systems that have potentially vulnerabilities and can be attacked by the red team. And then there is, for each blue team that is participating, there is one instance of such a network, or such a virtualized network. And there is one central red team that is running attacks against all these networks. And the red team is quite free to use whatever techniques they want to attack, but at least part of the attacks are run over a command and control infrastructure, in that case using the Cobalt Strike framework. So therefore, the setting for the red team during Locked Shields, even though it's only an exercise, it's very realistic. These are very skilled people that are experts for different types of devices. They know how to run attacks against these devices, and at least part of the attacks are run over a command and control infrastructure. On the other hand, we have the blue teams, which need to defend their network. There is one blue team for each network, and usually it's one blue team per participating country. And these blue teams, they can access the network that they need to defend over a remote connection, over a VPN tunnel, and they have some virtual machines, some devices where they can run their systems within the network that they need to defend. And these two things, I mention it because it's important for the approach that we developed. And these are two constraints. That first, the bandwidth that they can use to access their network is limited. So it's not possible to exchange large amount of data between where the blue team is and the network that they need to defend. And second, the infrastructure, these virtual machines that they can use to run attacks are limited in terms of computing power and in terms of memory. So it's also not possible to run very complex systems within this network. In general, also the blue team setting is very realistic, even though it's only an exercise. When the blue team arrives, the network is already under attack and some systems are already compromised. And as usual, it's they do not only need to defend the network, but they also need to keep its availability, because there are normal users that need to use the network for checking their emails or browsing the web or whatever. So just turning everything off, cleaning it, and starting it again is not a solution for the defenders. So that was the part about locked shields, and now I would like to describe the system that we use to, in that context of locked shields, detect command and control servers. We started by our goal, which was to have a classifier that can tell you, given network traffic, which of this traffic is command and control and which is other traffic referred to as normal traffic here. So in the end, we wanted to end up with such a classifier. In the beginning, we had as input data, we had the network traffic from the Swiss blue team, and we also had the recordings of the activities provided by the red team that we could use as a ground truth for this network traffic. As usual, in machine learning projects, we then split our pipeline into two phases. First of all, we had an offline phase for the training, which is done before the exercise and which is not time critical. And the second phase is the online phase, where the classifier is applied in real time to network traffic during the locked shields exercise. We further split each of the phases into 4 steps, where we first get the data, for example, from the recorded data of past year's exercises and from the reports that are provided. Then we need to do some pre-processing, which is more a technical detail to align the information that we get from the network traffic and from the reports. Then we extract features. Features are kind of properties that we use later to distinguish between command and control flows and other flows. We then come to the machine learning part, where we label the data. So we have a list of flows. We have all the features that we extracted for all the flows. And now we need to add a label. So for each of the flows, we need to say whether it is normal traffic or command and control traffic. And once we have this, we can use this information to select a subset of the features that we previously extracted. This is done in order to make the system more efficient and more performant. And after we selected the features that we used, we can train the classifier based on these features, and we end up with a classifier that we can then apply to traffic in real time that is captured during the exercise, where we extract the same features and get a label for all the flows afterwards, whether it is a command and control flow or not. So this is the overview of the entire system that we were developing here. And I will now go a bit more into the details of some of the phases here, starting with the feature extraction. Here we extracted 77 widely used network traffic features of 3 different categories. First, we had metadata, such as the flow direction or which protocols were used. Then we had time-related features, such as how long a flow takes or how many packets it sends per second. And third, we had volume-related features, which include features such as the number of packets or how many bytes are exchanged per flow or how big the individual packets are. So we have we have 77 features of this kind, and we compute all of them. We then have a list of all the flows and 77 features assigned to each of the flows. And we now need to compute the label for the flows. And this is fairly simple. We get from the red team reports a list of all the command and control servers that they were using. And whenever a flow either has the source or the destination as one of these servers, we label it as a command and control flow. And if not, we label it as a normal flow. So at this point, we have a list of the flows, features, and labels. And we can use this to reduce now the set of features that we need to consider to make the system more efficient and to make it run in the restricted environment of the locked shields exercise. And to reduce the set of features, we apply kind of a recursive elimination scheme where we first train a random forest model on all the features that we have, so 77 in the beginning. This then gives us a score for each feature of how much this feature contributed to the classification result. And we can remove just the feature with the lowest contribution, so the least important feature, write it to a list, and remove it from our set, start the entire process again. After the second iteration, we will remove the second least important feature, and so on, until we have no features left in our set that we use for the training, and we have a list of features ranked in increasing importance. And later, if we want to use the 20 most important features, we just take the lowest 20 entries of this list. So the next question now is, or the next task now is to train a classifier, and the question here is which one we take. There are many different classifiers usable in machine learning, and for our circumstances where we had one challenge, which is that while the command and control traffic is expected to be similar over many iterations of locked shields, the normal traffic is probably very different because the network might change a lot. So maybe one year it's a military airbase network, another year it's a network of a city. And we also have the constraints of the limited computing and memory that is available, and that we want to have a system that performs classification in real time, or at least close to real time. What we observed after trying many different models is that a very simple one works very well, and that is random forests. So these models are very efficient to compute, and they achieve good results, as I will show later. Okay, so now at this point we have our classifier, and now we can apply it in real time on the network traffic that is exchanged during locked shields. With this, I come to the third part of my talk, where I want to share some evaluation results. We did this evaluation based on two data sets that we obtained by the Swiss Blue team, and these are the data sets from locked shields 2017 and 18, which gives us the possibility to have two models, one that we train on the data from 17 and evaluate with data from 18, and the other one that we train on data from 2018 and test with data from 2017. Again, this is a very nice situation where we have two real data sets that are independent because they are from two different years of locked shields, and they are realistic because it contains traffic generated by humans, by skilled attackers and skilled defenders, which is very rare to be in such a nice situation when you do machine learning. We then trained these models. We tried many different parameters and found that these ones obtain good results. If we take random forest with 128 trees, each tree maximum depth of 10, and we take the 20 most important features. So when you do machine learning, the one important score for the evaluation, or two important scores, are precision and recall. And precision kind of tells you, if you get an alert, what is the probability that this alert was actually a true alert, so it represents really a malicious or command and control flow. And recall is if you take all the alerts that you get, how much of the command and control flows did you cover, or did the system cover with these alerts. And especially precision is quite important, because if you have low precision, it means you get many false alerts, and in the environment of locked shields where you need to run this in real time, and the defenders need to decide quickly whether or not an alert is true or not, it would be suboptimal to have many false positive alerts. What we observed is that our models achieve more than 99 precision and also high accuracy of 98 or 90% depending on the model. The next aspect that is important is the runtime, because we want to have the classification in real time or as close as possible to real time. And there, what we found is that on our machine, it takes about 3 microseconds to classify one flow, which is very fast. So now that I presented this approach here and that maybe members of the red teams are listening, they might ask themselves, how can we avoid this classification? So how can we modify the command and control traffic such that this classifier does not detect it anymore? And of course, this is always a problem when you do machine learning. There will be a talk later about adversarial machine learning. And we also did some steps in this direction. I think there is more work to do. But what we did so far is that we looked at what happens if the blue team can obfuscate some of the features that we are using to do the classification. So features like the packet size, timing aspects, or the volume of flows. And what we found is that up to 8 features, so we're assuming here the red team can choose the 8 most important features from our list arbitrarily, so we cannot use them anymore for classification. We observed that there is no impact on the classification result, and only if you modify more than 8 features, which is highly non-trivial in practice, then you would see the score dropping, at least in this data set. So that was it for the evaluation that we also have in the paper, and where you can find much more details in the paper. In the last 2 minutes, I would now like to share more insights about something that is not in the paper because it's very recent. And this is that the Swiss Blue team actually used that system in LogChiLs 2019, just a few weeks ago. And from the feedback that we got, we were happy to hear that it actually helped them to discover command and control channels that they didn't see by other means. And it also helped them to confirm alerts that they got from other systems, so maybe other intrusion detection systems. But because they had an independent source here of the same alert, they could be more certain that this is really a malicious server behind it, or a command and control server behind it. They used exactly the same models that we used in that we developed in our project. They use a slightly different way to extract the features because their workflow was slightly different, and this might have had a small impact on the results. But again, from the feedback that we got is that they were happy with the high true positive rate, and it helped them to detect command and control servers that they didn't detect otherwise, or to confirm results or alerts that they got from other systems. With this, I come to the end of my talk. I hope I could show you how we identified command and control channels at the example of the LogChiLs exercise. We did all these evaluation and development with data from the Swiss Blue team. We are extremely thankful for this collaboration, for that they shared the data and their expertise with us. If there are blue teams of other countries that are interested in testing this system or collaborating with us to develop it further, we are very interested in, and please approach us in that case. Also, if you have more questions, the first 4 authors of the paper are here at CyCon, and please approach any of us if you want to know more about the system, and I'm also very happy to answer questions now. Thank you.
Thank you, Roland, for your insights into detecting red team activities. We have the time for a few questions from the audience. Okay, the microphone is coming towards you.
Thanks for the talk. Did you try the model in a real world scenario?
Not so far, no.
Okay.
Because we don't have a comparable data set to test it there.
Oh, but you're just using the various features anyway. So would it matter if?
Yes. Well, there are papers that show that exactly random forests in other data sets that were synthetically generated work very well. So we expect we would have the same results for this other data set. but we were focusing here on the log shields and on the real data set.
Okay, thanks.
Okay, so
Thank you for the presentation. It's a pity that the domain controller people didn't perform better in our blue team, despite the fact that we had all this information. So the result was not so good. But that said, how dependent is the training set you obtain or the trained machine from the tools used by the red team, or how could one enlarge the number of recognized command control channels using other perhaps tool sets and attack tools?
You mean other command and control infrastructure?
Right, protocols, etc.
I think right now, so it's always what you train the system with, this is what you can detect later. So since we train it with this command and control traffic generated using Cobalt Strike, it will detect this. If we include other types of attack traffic, I would expect we can also detect other types of command and control channel. What is nice if you have this command and control channels is that you kind of can attack at the root of the problem and you don't get to the attacks that are probably very different, like to very particular attacks that cause different traffic depending on the environment in which you run them.
okay, we have a question from the back.
Yeah, cool presentation first. You used your tool just for detection or also for prevention to help the blue team? And the second part of the question is, if so, do you see adaptation from the red team?
Sir, can you repeat the second part of the question?
So this is detection tool.
Yeah.
But the added value is to go into prevention. What you detect as a CNC, you block it.
Yes.
With automation or whatsoever you want to integrate with solution. Did the blue team did prevention based on your observation? And if so, is the red team also evolving into the attacks, or it just launching the attacks?
So I'm not part of the blue team. I cannot provide all the details here, but from what I see, I think there was no reaction from the red team.
We did not do that.
Yeah, yeah. Mm. Yep.
Okay, we have a question here. Microphone is coming here.
Thank you for the presentation. At Ally Command Transformation, we are using machine learning to detect inside the threat detection and modeling. We never get to the levels of detection that you mentioned, like 90 and 98%. And the reason is that the let's say the radio of actual traffic versus the variability of common traffic on a network, it's simply too low. To which extent would you say that your measurement conditions are realistic?
I mean, they are realistic for the environment of log shields, for sure, because we have these two data sets, but I don't know how realistic they are to other, if you would have the same activities, but in a different network environment.
If you allow me to rephrase a question, if that airbase that you mentioned is a model of your network, if that was a real network on an airbase with a real traffic of different users, applications, and hacker intrusion activity, do you think that you would get by far to those detection thresholds?
It is the case also during log shields, during this exercise, that you have real user traffic and you have generated traffic to load the network. So it's not. I think the traffic is realistic and to some extent generated by real users. So I think from that I'm confident that it would work also in other settings, but I don't have results for that.
Let's take last question, and you can remember your question for the discussion round. Thank you.
Thank you. As far as I understood, you trained your system on one type of botnet infrastructure. Do we have an idea how many different types of botnet infrastructures are out there in the wild?
I don't have a number, but many, yes.
Too many.
Yes.
Okay, thank you, Roland. Okay. Okay. Next up, we have Dr. Roman Graf, who is a research engineer at Center for Digital Safety and Security at the Austrian Institute of Technology. He works on cybersecurity and data analytics topics, contributing to the development of several European research projects like Ecosian, Planets, Assets, and Scape. He has published widely in the area of cybersecurity and risk management. Roman has supported development of cyber threat intelligence solutions like Caesar, and also the one we all at NATO know and love, MISP. So his presented topic is very relevant to all of us who use Android phones, because as you might know, that even if you take applications from the trusted sources like Play Store, you actually can be 100% sure that it is safe. So Roman is going to try to explain how they're trying to make it safer. Please, the floor is yours.
Thank you. Hi. I would like to present our research about network-based technique for Android smartphone application classification. I prepared this with my colleague Aaron Kaplan from CERT IT and with my boss Rose King. At the beginning, I will briefly describe what is the problem, why is it necessary. Then I will explain two real-life scenarios, and I will turn to base of our research. It's a Drebin solution for APK classification, and then I will describe our approach for neural network for this solution. So why it is dangerous to upload malware? Because then user can lose money or his private data. For example, here is a porno player sample. So I should mention we got our samples from Icarus company, which is antivirus company from Austrian. And they have a lot of malicious samples and also benign samples. This is one of malicious samples, and it belongs to a Trojan family of malware applications. You will see in a red circle user has installed malware application because he was motivated by word porno, and what does it make, this application? It sends expensive calls to expensive SMS to some numbers, as you see. I will show you source code later and also why we found it out. And why it is possible, because user gave permission by installation to do it. He hoped it would be interesting application, maybe. So it's a source code, and with red color I marked important parts of this source code. You see it is SMS for these expensive numbers. And it's our features. I will explain in details more how we get them. But you see also marked in red why we our approach decided that it's a malware application. So the second sample is a fake Netflix application. You see user also tries to install Netflix and expects that it is a media application to see videos or something else, and application asks him to insert password and login. Then it give note that hardware doesn't match to this application. He should deinstall this. But if he doesn't want to deinstall, it will try to do it by itself. And in the meanwhile, already his login data was passed to a malware server, and he has lost his data. And in this sample, we found out that it was AES encrypted, and key was interesting. It was in source code in plain text, almost just a little bit encoded. And for this application, only one thing was important, that application could connect to internet. So you see it's also marked in red key, and also encoded URL. And below you see it's URL to, if it's decoded, it's URL to a malicious server. There are multiple permissions that user provided, but actually attacker just needs only one marked in red, so HTTP post and internet connection. Our research started from a paper of Drebin project done by another researchers, but very famous research. And Aaron with his students provided further research and applied support vector machine and compared to other machine learning algorithms in order to improve the results. The idea of this Drebin project was to classify malware application for Android and to distinguish from benign applications. This approach was good because, as you see, we have different features split by groups, and then they created a vector and classified. And at the output, they could say that it's possibly a malware application, and they could explain why, because all features belonging to these malware families are in plain text readable. Feature sets are combined in some subsets. You can see a brief list. Actually, Android package contains a manifest file, and some features belongs to this manifest file, and for other part there is a source code analysis, and also it contains different groups, subtopics. Here are some samples of malware families and associated subsets of features. Features are actually plain text, and we analyze plain text. But it was in Drebin publication. So support vector machine provided good results. It was up to 97 accuracy of true positive rate. Previous speaker already explained this estimation method. And false positive rate is about 1%. But it was a huge feature set, and that was really a problem because for our sample it was 200 gigabyte of RAM, and that's why we decided to try to find another approach and developed a neural network approach. It is good because it requires less RAM, but problem is that it's not explainable. As you know, possibly that mostly neural networks are not explainable because there are neurons that have weights. Weights are initialized randomly, and then during the training they adjust the weights. So it's not explainable. There are some attempts to make explainable neural networks, but again, it is making explainable with another neural network. So we don't really can explain this. And we have sets of samples about 1 terabyte now, and it's about 56,000 of malware samples. It's our approach overview. We have a situation awareness system, and we get APK, so application code, and we use Drebin code is not public actually. We use source code of Singapore researchers that who try to repeat this code according to Draven publication. Actually, it works well, and we get features using this code. Features are, as I said, some text, and then we parse it and prepare our feature model. We split our set of samples into training, validation, and test sets, and we trained our model with these features. I'll explain later in details how we do it exactly. And additional part, what is important, these applications during the time changes. So also attacker methods changes. Earlier it was SMS, now it is not more SMS, some other methods. That's why it's not possible to train just one model. And we decided to train different models, distinguish it by different rules. For instance, time, or from where we get these malware samples. So, and each of these models is in situational awareness system 1, 2, or 3. And then we share our results with people who requested it. We plan that we have a service where somebody can upload application and check if it is already known that it's malware or not. We employed word embeddings method in our neural network because it's one of the best to analyze such text features. How it works, text cannot be analyzed by neural networks. That's why we convert it to arrays into numbers. And then, for instance, if we would have a sentence, CyCon is very interesting, very helpful. So we would give index for each word. If word repeats, then it has the same index. And in the next turn, we convert it to embedding vector, which is where we can just provide the size, and it will be done automatically. And you have seen, you see here a sample of this. It's just some numbers then, but it's a vector. And for each file, we create a list of such embedded words. And that is input for our neural network for train. Here is our workflow, how we train it. As I already mentioned, we get feature first, then we check if it's already in our trained model or not. If not, then we add it to the model and retrain it. If yes, we just query the model and then go through a rule engine, as I already mentioned, and provide a classification result if it's malware or not. Here is a brief overview about our rule engine. We have, for instance, just sample rules. For instance, which date, which operation system, which vendor produces APK. And applying these rules, we could additionally improve quality. If we have additional knowledge about something, then we could implement it in such rule system. So these blue icons are if statements actually, and they produce a conclusion, and we aggregate conclusions and go to results in some conclusion. Our neural network has different parameters, such as learning rate and vector size, maximal vector size, embedding vector size. Then we have training loss, training accuracy, validation loss, validation accuracy. And combining different settings, we analyzed what is a better performance for our model. And in result, we have a list of true positive rates and false positive rates. So then we can estimate which setting for particular model provides the best accuracy. Here is a summary about neural network training process. You see, we can provide how many iterations of training we will do. So here is 5 iterations, it was enough. And you see that accuracy training accuracy and validation accuracy constantly increases and then is fixed at some point. And error, validation error and training error, as expected, are reduced at the end. And we used input layer, then we flattened this input data, and we used additionally hidden layers to calculate our model. And sigmoid was the activation function for our training model. This is relative operating characteristic that also provides visual result of our calculations with different settings. So on the right, in the right part above, in the upper side, you see the perfect classification point, and this red line divides good results from not so good results, and you see that all our results are located on the left side in the higher part. So we can say all of them are quite good results. And so perfect classification point is on the x-axis. It's near the 1. So the near to this point, the better is the result, actually. So I can conclude that we developed real-time automatic solution that classifies APKs in malware or benign, and we combined rule engine, feature extraction, and neural networks to achieve this decision support method. And I would like to thank Icarus company for provided samples.
Yes, thank you, Roman, for trying to keep us Android users safer. We have a time for a few questions. Oh, there is a question.
Thank you very much for your great presentation. I have one question. Have you been able to test APKs that actually passed the Google verification test and ended up in the Play Store? And if so, have you been able to detect malicious apps that ended up there?
No, it's just a draft, so prototype, and we just used samples that we got from the Icarus company. We are just related on these samples. Okay. Also, it was important to compare because we wanted to compare previous calculation with support vector machine, and if it's new application improves previous application, and previous application was trained with the same data. To have the same, to have ability to compare them, we need the same data. But we are working in one project now, and we want to collect now much more samples, and would like, if somebody can provide especially benign samples, so we would like to try our model on these new samples.
Yes, because it would be interesting if this would be an additional layer on top of the standard verification procedure.
Of course. Yeah.
Okay, thanks.
Okay. Another question?
What kind of neural network did you use? Like a traditional, let's say, shallow neural network, or you went into deep networks?
It's deep neural network with word embeddings.
Sorry?
It's a deep neural network with embedded word embeddings.
Okay.
Word embeddings is a general approach for this.
Okay. And so if you use a deep neural network, weren't you concerned about the size of the trained network and the computational power required to run it on the actual phone?
Yeah, we run it on a server with Hadoop and GPU, but currently we don't have so much data. It was not a big issue. We will look at that problem later when we have more data, but actually training itself was quite fast.
Training, yes, but what about deployment? Because SVM is a very compact model once trained, whereas deep neural network can be fairly large, even when trained. I mean, so.
Yeah, but we have split it in different smaller models, and we will also apply this rule engines that we select which model we apply, so it is not so big anyway.
Okay, thanks.
Okay, we have another question here.
Roman, was any a priori information known, any contextual information known to the classifier?
Actually, not. We just looked some samples.
So you didn't know anything about the nature of the applications?
No, we just, but we, of course, we had a labeled set provided from Icarus company. They have possibly their rules and methods, but we just use this sample.
So was it the classical unsupervised learning, yeah?
No, it's supervised because we had labeled set.
Also, you had something known.
Yes, but it was provided by Icarus, and how they decided it, it's their rules. We don't know these rules. But we already had a labeled set.
Okay, thank you.
Okay, I have another question here.
Thank you for the presentation. You showed a very high accuracy of your system, and then you told us that you tried your classifier on several hundreds of gigabytes of APK. But what was the size of the labeled data in order to train such great classifier?
Labeled data was 56,000 samples, the size. It's not so extremely big, but now we got bigger size. We will proceed with this. Yeah.
Okay. Do you have any other question? No? Okay, then I will ask you one question. So what should the adversary do to avoid your detection? Can adversary just take most popular common application from Play Store and add some unknown malicious code that was not previously used anywhere, something custom?
Yeah. Our analysis is static. Of course, if people produce customized applications, they have chance to circumvent our model, but it's quite complicated because we also don't know by ourselves which features we analyze them automatically, and there is possibly a chance to circumvent it, but possibly not if this customized code has some specific features that we already had in our trained models, and it also will be detected. So if you take already known code, it possibly will be detected and just adjust it somehow.
Okay, thank you. No more questions, then we can continue. And our next speaker is Michele Colajanni, who is a full professor of security of engineering at University of Modena and Reggio Emilia, Italy since 2000. His research interests include system and network security, scalable and reliable architecture, and security analytics. He directs the Research Center on Security and Safety, the Cyber Academy for Ethical Hackers, and Masters in Cyber Defense Governance for the Armed Force and the Bologna Business School. Today he is presenting possibly one of the most important topics for the future of cybersecurity systems that are based on machine learning. So adversarial attacks against them, which are trying to poison machine learning algorithms. Please, the
Thanks
floor is
very
yours.
much, Artur, for the kind introductions. So I can leverage the third position because my colleagues already presented all the technical details about machine learning. And so I will try actually to answer the main question of this session, if artificial intelligence, machine learning, and learning can help us now and in the future. So just a precision, because I'm sorry, I'm a professor, I need to to clarify all the terms. So, because some people say, okay, artificial intelligence is 60 years old. This is not true. Because in the first part, what we can call the artificial intelligence 1.0, we tried, our goal was to teach to the machine to resonate. So we define ontologies, semantics, a lot of formal methods for reasoning. And actually, it didn't work. But in the last 10 years, we changed completely the approach. Now we are trying to teach to the machine how to learn. And this approach is working much better. The novelty is also a technological novelty. We have a huge amount of data, huge computational power, and so we can introduce a lot of fancy algorithms, machine learning, deep learning, and whatever the other colleagues explained. So another point that we should clarify is the real priority, the real importance of all these methods. In my metaphor, artificial intelligence is like a refinery. But the refinery is useless if you don't have oil. And oil is represented by data, an ocean of data. You need a large amount of data. And the declaration, the claims at the end of this slide are clear. Which is more important is the amount of data, and the type of data that you choose for machine learning to train your systems. If you made a mistake there, the output is wrong. Trash in, trash out. So you need a huge amount of data, a huge amount of useful data. And data is not the reality. Data is just a portion of the reality, is a representation of the reality. So if you look at this picture, you look young people, smiling people, we look at the data. So the definition of these people is not the reality. Nevertheless, artificial intelligence works. There are several problem domains where artificial intelligence works. And this doesn't mean that artificial intelligence works everywhere. So artificial intelligence works very well in computer vision, in speech recognition, text interpretation, analytics, microprofiling and neuromarketing. That's very perfect for profiling each of you. Works very well in games. Chess, you remember, Deep Blue. Then Go, and even poker. That is an interesting game because you have a partial information about this game. On the other hand, all the pieces of the chess are on the table, so it's a different problem. And actually, artificial intelligence now helps a lot the bad guys. Artificial intelligence is used for malware production. Artificial intelligence is used for chatbots, for information warfare. So there are several problem domains where artificial intelligence actually works and improves year by year. But which are the common features of this problem domain? They are clear definition. They have rules. You can have an optimization vector because you know when the problem and the solution is a better solution in comparison to the previous solution. On the other hand, I think that we are working on the most complex domain. We have no rules. We have no border definition of our problems. And even worse, we have to model human behavior. We can model in a certain way, in a precise way, the machine behavior. But what about the attackers? What about your people, the user of your machines, the insiders? I mean, it's very, very difficult. And there is a third problem. We are facing a continuously dynamic problem. The other problems are static. If you have to recognize a cat is always a cat. In our context, the data changed, the problem changed, the system of a medium-large enterprise changed continuously. So we have to face this very well-known problem that is a concept drift, where we don't know the real correlation between the inputs and the outputs. And this correlation evolve over times. And we have another problem that the other presenter explained. We have a lot of good samples, even in networks, and very few malware samples. So actually we can train the machine to recognize the good, but it's very difficult to recognize the bad because we don't have enough samples. And if this is not enough, and this is my last challenge, is we have adversarial on the other side. And this is much, much worse. So someone said that this is the direction. I mean, I agree that this is the direction. The static solutions, the antivirus, the static antivirus, the typical pattern matching solution don't work anymore. The typical rules for devices, firewall, or whatever, don't work anymore because we are facing a continuously evolving domain. So, and we cannot manage, the human cannot manage all this amount of data. I mean, it's normal to have in a company something like traffic 20 millions of packets per day. I mean, there is no way. We cannot manage. So we need to go, this is the direction. The problem is that the attackers are human, are smart, are motivated. And so they know that we are changing the detection rules. We are changing the devices. And so they are also improving their attacks. They know and they are studying how to evade the dynamic rules that we use for detections. And the adversarial attacks is very well known. Professor Vincentelli already explained it in his great talk this morning in adversarial learning, when with few introduction of pixel, the same algorithm that in the first part, on your left part, was able to classify exactly a cat, on the right part, with a small number of pixels that you cannot recognize, was recognized as a guacamole, is a South American sauce. That in some sense, if you know, it's not so different. There is some gray part, it's some difference. So, extremely new, is extremely challenging. On the other hand, the problem with adversarial attack on cybersecurity. So, in the paper, we tried to introduce a small taxonomy. It's not a very huge taxonomy, because the adversarial can intervene, can influence the data set. So if he knows which are the main features in a random forest model that I use to recognize, to classify a malicious packet, he can introduce small changes, very small changes that are not recognized as an attack, but that change the training of the continuous training of the algorithm. Or he can use the same approach at the operation time, at the test time, where there is a trade-off here. If you want to detect adversarial attack, in some sense, you have to enlarge the data set. You have to have a larger data set that is recognized as an attack. But if you enlarge the data sets, on the other hand, you have a lot of false detections. So it's a difficult trade-off to find the right definition of true attacks and false attacks. It can violate the data set, the integrity. It can introduce a lot of packets just to arise a huge amount of alarms that force, in some sense, the system operator to turn off the detectors. So since the first presenter discussed about random forest, my example is on the same direction. Random forest is, in this case, is a good detector. A simplification for our problem is that we need just a binary classification, because random forest can be used also for larger sets of classification. On the other hand, we need just a binary classification. So the idea is that original random forest uses static parameters. And This is fine for the static problems. But in some sense, our problem domain is more fuzzy. A packet can be malicious or not. So it can be malicious with some probability. So instead of reducing the probability part as a deterministic part, we preserved the probabilistic part. And in some sense, we could have a first part of a classifier with the probability that remains in the model, and then we train the system with these flexible parameters, and then we use in the test part. The interesting point is that you need to continuously update and train your model. If I can keep your question, this was an interesting question about can the random forest can be used in another network? I'm sure, I can guess that it will work in another system, in another network, with a different traffic. The question is, what if CyCon 2020 will use a different botnet, a different malware family? This is the real question. And we don't know. We don't know. I can suggest that we have to change, otherwise Switzerland will win. I mean, they have good support. So first hint is to change because they are ahead. And the result, what about the results? I cannot sell you anything. On the table, you have the data set. The data set is extremely realistic. We have something about 1 billion packets. I mean, normal traffic, where we introduces 13 types of botnets, so 13 types of malware. From this table, you can recognize the problems. We have a number of net flow in terms of millions, but the malicious flow are 2 or 3 orders of magnitude lower. Do you remember my problems? How I can train an automatic, a machine learning thing with these few, in some sense, packets with respect to the normal net flow. And okay, I can present just the last results where you can appreciate that our algorithms works much better than the state of the art because our results are always on top of the previous result, and the detection rate is high in some sense. But I want to say the truth, all the truth. And if you look at the entire picture, that is the 13 or 14 histograms, top right, where an adversarial attack could change some parameters of the features that we used for detection. So there are the first 4 histograms, the adversarial attack could change just 1 feature. So in the second set, it could change 2 features, and so on until 4 features. And the final results is what we expect. Is a continuous decreasing and decreasing. And this is the truth now, today. Now, we can improve the state of the art. Research is based on this, a continuous improvement. Please improve our results. So the truth is that there is an assumption behind the scene. The assumption is that what is anomalous is also malicious. And what is malicious generates an anomaly. But unfortunately, this is not always true. So we have false positive and false negatives. And would you buy a detector that is precise at 99.99%? Four nines? Will you buy it? Yes or no? Why not? So come on, 99.99. No, it's yes or not. It depends on the number of flows, number of packets. If you have 10 million packets per day, that is normal. 99.99 means at least 1,000 false alarm per day. And you cannot manage one. If you no, so we don't need 99. We need 99. I mean, at least 5 or 6 9 precision, and we are not yet there. This is the truth. This is the truth. On the other hand, so positive message. Even the biggest cloud provider, Microsoft Azure, Amazon, Google, are using the same technique. So because, as I said before, the direction is this. There is no alternative. So this is the direction. And they have much better results. But they have much better results because they have huge, huge amount of data. They don't have millions of data. They have billions and billions of data per day. So, summary, either you can define and limit your problem. Otherwise, you need a huge amount of data to have better results. And to conclude, these are not my requirements, especially the fourth one. So we need fairness, explainability. This is an important point because most of these deep learning algorithms work, but we don't know why. We don't know why. And DARPA opened an interesting project about the explainability, why we want to know the motivation. If we want to apply this algorithm in the society, in the real, we want to need the motivation, why these algorithms work. They should be robust to an evolving data set and even robust to adversarial attacks. The fourth one is scaring for all the technologies people that are around, not for the lawyers, because they are trying to say, the Organization for Commerce and Development, they are trying to say that organizations and individuals that operate and deploy artificial intelligence should be accountable. Should be accountable. When should will become must, I will go fishing and sailing, because this is dangerous. I mean, I agree that the society, the real world, want this accountability from us, but this will change the industry, because until now, 50 years, 60 years of computer science, computer and software industry has never been liable about their mistake. We produce beta testing products that are not products. You accept patching every week, every month. This is not possible. When artificial intelligence and the software will become an important part of this, already became an important part of the society, of the Internet of Things world, accountability, liability for the computer industry, but even for us that want to apply this, is an important part. Thank you very much for your attention.
Okay, thank you, Michele, for enlightening us about problems relating machine learning in security systems. We have time for a few questions before panel discussion. Do we have any? Oh, there is one question there.
Sir here in the back. I really appreciate your talk. I was just wondering, as far as obstacles to, I'm back here. So.
Yeah, we are.
We have lights in our eyes.
I should stand up. I'll stand up. As far as obstacles for improving our ability to use machine learning algorithms, would you say that our ability to process large quantities of data is the bigger obstacle, or our ability to understand and articulate to the machine learning algorithm what it is that we're providing as inputs?
No, sorry. I didn't say that the impossibility to provide, to manage a huge amount of data is our limit. Our limit is to have this huge amount of data for training, to continuously have this amount of data for training. I don't think that the architectural part, the machine part, is the limit today. I mean, the hardware is, and the memory is always and always improving thanks to our electronics colleagues. It's not that the problem. The problem is how you can get this data and how you can manage continuously changing. Because, I mean, as we are working in an evolving model, I mean, the chess are rules, the cat is the cat, the text is the text. But on the other hand, I mean, the typical approach that they have, I use 1 billion photos or billions of text, and then I can train the algorithms on this set, and then I can use the results for new text that I didn't see before. I mean, in these scenarios, the algorithms work, but in our scenario is not that. Our scenario is a continuously changing scenario. So it's not only to manage a huge amount of set of data now, but to manage a huge amount of data now, tomorrow, next week, and so on. And actually, there aren't enough tools that, not yet. I mean, this is an opinion. For us, it's a dream. I mean, any problem for a researcher is a dream, no? Because we have problems to solve. Please.
There are a few questions in the middle.
Oh, you need the microphone. Yeah.
So I was curious about whether or not anyone is actually attempting to develop and use adversarial models in the real world to attack machine learning systems, or when you think that might happen, and kind of what industries would be the focal point for that.
Okay. Do you want the truth, all the truth?
The truth, please.
I don't know the truth, so it's my opinion. The adversarial attack, I mean, the attacker now don't need, not yet, because, I mean, even the best machine learning algorithms work at 99, and as I said before, 99 is not enough. So they don't need. But what I can say, if you use automatic attack, botnet, they use automatic communication, standard communication, we can, in some sense, address the issue. If there is a human behind the scene, a competent human behind the scene, he wins. I mean, as usually, he wins.
Thanks.
Okay,
please.
There's another question right here. Yes.
Could you expand a bit more about this principle of accountability that's being developed? Because from what I understand, from what you explained, so they could hold the person operating the algorithm responsible, but then that person doesn't know how it's been developed. So if I understood what you were saying.
Sorry. No.
No, okay.
Can you rephrase in another way?
Yeah, sure. When you were talking about AI accountability, there was something up there about holding the person, the people developing, deploying, and operating the AI systems.
Yeah.
Would they hold the person operating the AI system responsible even if they hadn't developed it? So that person might not know how the algorithm's been developed.
Okay, luckily, this is just a proposal.
Okay.
Just a proposal.
Right.
But, I mean, law system, the society wants this. I mean, there is a famous example, deep learning algorithms that recognize wolves from dogs better than humans. But they didn't know why. And after months of research, they recognized that the machine didn't look at the animal. The machine looked at the environment. So an open environment, the woods, is recognized as a wolf with high probability. In a domestic, a city environment. But they didn't know. The machine learned by itself. I mean, in some sense, this is real intelligence because they didn't know at the beginning. But, I mean, we cannot accept in the defense, in the society, in the military space, something like this that works. Just works. No, it's not enough. But it's just a suggestion.
Okay, there's another question. Yes.
Thank you. Professor, I particularly like your slide 13.
Oh, 13?
The one
Sorry, can we go back to
among all the others, it basically says that we are looking for anomalies.
Yeah.
For us in particular, we have an approach that works much better, which is based on data representation, data filtering, data preprocessing. When we are talking about forest algorithms or algorithms based on classification, we find extremely useful if we don't let the neural network run wild, if we pre-pattern the information, like using a framework, like using Fourier transforms, Gabor transforms, whatever, to patternize the input set. In those cases, as I said before, we don't get to 90%, we don't get to 98%, but we get to rates that are pretty robust against change, meaning that when we change the data set or we change the adversary behavior, the machine is still useful. It doesn't go from 90 to 0.
Do you agree with my last comment? My suggestion, combine multiple methods. I'm sorry, I didn't present the last claim, but I completely agree with you. We cannot have just one approach. We have to combine multiple approaches. I agree perfectly with you. This is the direction.
Thank you.
Okay, thank you. You can take your seat and we will move into panel discussion. So let's take first question for panel setting.
Actually, my question was
Oh,
so much about
okay. Okay, microphone is here, please.
First, thank you very much for interesting talk. And I do have a kind of follow-up question. Actually, it's not a, question, but rather than as a statement. Again on this 13 slide. and the statement that any detection of an anomaly may lead to a malicious attack, which is pretty true, but I would caution not to generalize these principles because in AI area, in learning, we actually, for example, let's say emergent behavior of complex systems. In principle, the emergent behavior leads to discovery, to new forms of species like in evolution, and they should be considered like a positive feature rather than something negative. So yes, your statement is correct in this specific domain, but not to generalize in other systems and processes.
If I can generalize your comment, it's true. I mean, what we have to understand is not just a model that is trained and then a model that is applied, but a model that is trained, that is applied, that is continuously improved, and so on, and so on. In some sense, the training part will never end because some emergent feature can be evidenced. Even something that you didn't think about, or some correlation that you didn't think in advance. I mean, is some sense one of the most challenging problem setting that we have, because different data, different attacks, different system, because our system change continuously. And even without adversarial attacks is already a really complex problem. Is already a complex problem. Then a continuous improvement, a different model, the integration is the only way. I mean, it's easier to say than to implement.
Okay, thank you. Do you have topic for discussion? Yes, please.
I'd like to know, just in general, what the panel thinks the impact of quantum computing would have on their different models and machine learning and all those. So quantum for all three of you. Thank you.
Yeah. I missed quantum computer and blockchain, if you want. Okay. Quantum computer, if my colleagues want to explain, there are two. Quantum computing it can be divided in two different parts. One is quantum communications for transmission that already works. There was an interesting experiment from China, satellite, two platforms, one in Switzerland, or the other in China. So quantum communication already works. Quantum computing is ahead. I mean, the problem is still a problem. We are improving, but we have not only to improve the hardware part, but then we need a lot of software. We have to change completely the software. So it's not something that will be there in a few years. This is on the other hand, our community, not me, already are working on post-quantum cryptography. So the academic research is already trying to face the issue of tomorrow. As far as I don't know if you have more.
Our company is working on quantum cryptography, but for artificial intelligence application, I don't know now. It's not developed yet, the hardware and so on. It's too early, I think.
Okay, another topic here.
Thank you for your presentations. A question for the panel. It's an open question. In what way would you think that machine learning would be helpful in attribution of attacks?
Please, Martin. Raymond, so, yeah. I know.
I'm not sure. I think for that case, it's even much harder to get the data sets with which you could train such a system. So I don't see a straightforward way to earn a promising way to use machine learning there, but maybe my colleagues have more ideas.
I think attribution is...
No, sorry, please go ahead.
No, I think attribution in general is very complicated problem. It's very hard to say. Artificial intelligence depends on data, and if data is wrong, you can produce wrong attribution result. It's dangerous.
Attribution is the problem. Because all the international community is based on this fundamental. And the problem with attribution is not only, we can easily artifact the source. There were attribution because there was some comment in Islamic language. Come on. Anybody can introduce some Russian comments. It's not enough. It's not enough. I think that these models can help to circumvent the problem. Something that should be in this area because they use this tool, but then you need other means. You need other means that other approach. Again, is a combination. A digital investigation cannot be just digital, not just based on digital, because an attack. I don't think that there are any people now that say there build a completely new malware, a completely new botnet. A new botnet is a combination of different parts that are in the wild. So the attackers typically add some software, combine, add some masquerading, some new cryptography, but most of the software is already there. So can you say that? Okay, no, it's not the environment where I can say this. Okay. I can tell you in private. I cannot.
Sorry,
there is a registration. There is a registration here, and
Thank you.
I don't like polonium.
Thank you. Do we have another topic to discuss? No, then I will ask you a final question with expected one-sentence answer. Should we be concerned about machine learning in security systems in 5-10 years? Are we going in some dangerous direction?
I mean, the direction, as I said, the direction is this. There is no. The problem is the finish line. I mean, we are not arrived on the. Probably there will not be a finish lane. I mean, the society should decide which is the autonomy that we want to give to the machines. I mean, this is the real question, and not only for security. How much the machine can take the power. In games, they won. I mean, in chess, Go, poker, they win every time. So they are better than us. In other contexts, they are better than us. Health system, image recognition, they are better than us. In other open environment where the decision is not clear, when we cannot apply a clear optimization function, because all the machine learning is actually data and optimization, and continuous optimization. If we don't have this optimization function, if we don't have the ground truth, we have a problem with the ground truth. We cannot compare the previous results with another one. It's difficult. The problem is not of the machine learning. The problem is our problem that decide to outsource this decision to a machine. It's not a problem of the machine. The machine does whatever it can, but in some areas, before quantum computing, that will open new issues and will open over new solutions. We are in the middle. Now there is an interesting case. I don't know if it's Japanese or Chinese, that he lose $20 million because the algorithmic an algorithm for financial investment made mistake. He wants to sue the algorithm or the products. So it's something strange. Can you sue an algorithm? And it is related also to the problem with assignment, to liability. I mean, there are interesting open questions that the society, lawyers, politicals, and the technology we have to solve. I mean, I don't have the solution. I don't think that anybody here has this is the solution. We have to study. I mean, if there is a positive effect of this Congress, is that we can collaborate, we can discuss from different cultures, and this I think that is the real direction, to discuss together.
Okay, thank you. Roland, do you have any concerns about future of machine learning?
I think it depends on particular challenge. In some cases, it's very good applicable, like image processing. In some high-risk tasks, maybe it's too dangerous because you will not get 100% accuracy.
Okay. Roland, any final thoughts?
I think we are, at least in cybersecurity, it's not that we need to be worried about what machine learning does. It's more that we need to be aware that machine learning probably does not do everything we want, and it's always machine learning more helps to fight against things that we know or that happened in the past. And if we have, on the other hand, skilled attackers that do things that we do not expect and that our machine learning does not expect, we cannot expect the machine learning to defend us against everything.
Okay, thank you. Let's give a round of applause for